Thank you, Jane. So this is the third and final hour of the Mike McCarthy show. I think you'll probably all be glad to know that. More seriously. So what I want to do in this lecture is talk about, in some sense, a new area, at least for us, and I think more generally for the field of molecular spectroscopy, where we're going to try to do something called, well, I would call it just generally complex mixture analysis. And we want to take it to the extreme whereby we're going to try to assign, in a wideband spectrum, everything, literally every single spectral line that we observe, we want to try to assign. That's the goal, at least. All right? So, again, going back to yesterday morning's talk, there's basically, in my mind, you could kind of simplify it, but there's basically two approaches to discovery. There's actually three. The third one being if you find a strong unidentified line or sequence of lines in space, trying to identify it by that means. But in the laboratory, by far the vast majority of people who do spectroscopy, who do astrochemistry, molecular spectroscopy, use what I call conventional methods in the sense that everything is based on a calculation, on a model, on a desire to detect specific species or isomer or ion. And that's focused normally, generally very narrow focused, and it's almost always on a basis of combination. And as we saw yesterday, it's been wonderfully successful. Many species have been found by this approach. But in doing so, you ignore almost always everything that doesn't fit the criteria of the model you're basing it on. In wideband spectroscopy, we're going to record very quickly, or fairly quickly, a very wide spectral range. And then we want to assign everything. The problem there is we have potentially a lot of information, but we don't have any knowledge. Right? We have all these spectral lines. The question is, what is it there to these spectral lines? So that's really the challenge, right? And it's particularly true in spectroscopy when you look at astrochemical systems, because as we talked about yesterday, and I'm going to talk about, for very few of these species, is there a clean, simple synthetic method. All right? So instead, we produce nearly all of these molecules in this very rich broth that produces familiar and exotic molecules, and using these non-specific techniques. I'll talk about electrical discharge, there's laser ablation, electrolysis, what have you. Right, so is it too ambitious to want to ultimately be able to do this? And ultimately, this is then simply if you will, encompass mixture analysis and information theory. But the key here, of course, is that this is rotational spectroscopy is the structure-based method. Right? So we want to move away from this mindset of kind of the one line, one molecule at a time. Like I showed yesterday, right, where we're going to specifically focus on one transition and select it, we're going to optimize everything, and ultimately try to find it, and move into this kind of reaction chemistry perspective, where we're going to set up conditions, we're going to optimize on a molecule, and then we're going to record this wideband spectrum. All right, and the key here is we can ultimately do this because we have a structure-based rule. The rotational transitions depend upon ultimately the lines of motion. So the approach that I'm going to describe is using two techniques in parallel, or not in parallel, complementary method, which we record this wideband spectrum and then do follow-up measures with a narrowband spectrometer. And we're going to access this huge number of resolution elements that are available by wideband spectroscopy. And I would argue, I would convince you that the obstacle to doing this analysis is really technical in nature. It's not fundamental. Right? So what we really want to do is develop these rapid, exhaustive, and empirical analysis tools. And really the holy grail, so to speak, is what they call library identification. Right? So every analytical technique relies on libraries, comparing your spectrum that you measure to a library. And that's how most identifications are made. Of course, in rotational spectroscopy, we have the ability, as I showed yesterday, and other people have shown, to detect new molecules by virtue of the rotational spectrum. And if we could do this, there's potentially broad applicability in other areas, right? So we're just doing this because we want to understand the rich chemistry that's in space. We have rich chemistry in laboratory, and potentially that could be useful in other areas. But that's not really the focus. All right, so this comes to this very famous quote, at least for the older people in the audience. And this is how I identify.
Or senior.
What's that?
Or senior.
Or senior, I'm sorry. I should say. Junior and senior. So, some of you may know who Donald Rumsfeld was. He was the defense secretary under George W. Bush. He was at a threat assessment hearing, and he was asked about threats. And this is a portion of his statement, which was widely panned in the press. And he goes on to say, there are known knowns. There are things we know we know. Fair enough, okay. There are known unknowns. That is to say, there are things we know, we now know we don't know. But there are also unknown unknowns. There are things we do not know we don't know. Right? And, you know, you can imagine how that was received by the public and the press. But if you think about it, it's actually not as crazy as it sounds, especially with at least respect to rotational spectroscopy. So, known knowns are things which are well characterized already, right? They've been measured by some technique in the past. We have catalogs for them, and we can simply compare our complicated spectrum to the spectrum of these known species, and we can make identifications. Known unknowns are actually things that we plausibly can infer are there, but perhaps have not been measured, right? So, for example, there may be a rare isotopic species or something. We have some molecule, and we observe it with signal noise of 1,000 to 1, and carbon-13 we know is down by 1/89, so we can plausibly expect to see the carbon-13 natural lines. Right? So that would be an example of something where we plausibly can infer it's there. But what's really interesting are these unknown unknowns, right? These are things that perhaps no one's ever calculated, perhaps no one's ever done any experiment on. But they may be written down very well, right? And so that's the beauty of this kind of analysis, is that we can do it in an unbiased way. We can simply, ultimately, the goal of which is to identify everything. And in doing so, perhaps there are lots of molecules that we can find that have never been measured before. And maybe those are astronomical. So, one of the major so part of the effort in our group is really this complex mixed analysis. And what I want to show you here is just one example where we can apply it to we think, a very important astronomical problem. And this relates to the question of where are the aromatic rings in space. Now, in organic chemistry, which is where I think there's some background in chemistry, you know that 5- and 6-membered rings are ubiquitous. Right? If you look in the Chem Abstract Service, it's even in the logo, you have these benzene rings, right? And I looked it up, and we can argue with the exact number, but it's something like 50%, maybe as high as 80% of the 135 million compounds, this was as of probably a year or two ago, so it's 140, 145 now, contained a ring. But in space, there's over 200 molecules. Among the polyatomic molecules, 175, and there are 20 that are acyclic, which have a comparable number of carbon atoms to benzene, and those are shown here. People have looked in the past for, obviously, benzene doesn't have a rotational spectrum, but there's derivatives, there's stable heterocyclic rings, pyrrolylene, furan, people look for coriandolene, which is a third of a lucky ball, which has a very rigid structure, it has a big dipole moment. Everything's fake. Okay? So it's been an oddity. Part of this is a selection effect, right? Because these are all linear or nearly linear chains, so we have a very simple rotational pattern. That changed about 2 years ago when we and our coworkers reported in space in this source TMC, which I mentioned before, other people have mentioned, the detection of the simplest aromatic cyanide, which is benzonitrile. So that's a benzene ring which we replace 100 down with a CN group. And in doing so, impart this molecule with a very big dipole, and make the rotational spectrum quite conspicuous relative to other molecules. Right? And so we did this with a GPT. I don't know if anyone's shown a picture, maybe Suzanne showed a picture. But this is in Reed Bank, West Virginia, the radioquiet zone. This is 100 meters from this side to this side. So that's a football field. It's huge. It's the largest steerable object on Earth. All right? And what we found when we looked with this very large radio telescope, very weak lines of, again, cyanobenzene. And it's a little bit hard to see, but you can see on the monitors a little bit better. In black is the astronomical spectrum, in red is our simulation based on the laboratory data. Right, so there's perfect agreement. We can use something called spectral stacking, where we stack up all the lines together, because we have, again, the uncertainty in the laboratory frequencies, the fraction of line from the source. And you can see this 80-some sigma detection. And it has a little bit of structure here because this is because of the velocity structure in TMC1. All right? And so what's neat about that is it actually implies, we obviously can't see benzene, but we can see cyanobenzene. It implies the existence of benzene in this source. And the argument goes as follows. There's CN radicals very well known in this source. And people have colleagues have looked both theoretically and experimentally at this reaction, in which benzene reacts with CN radical. And there's two ways you can add the CN to the benzene. You can add it to form the cyanobenzene, which is the bluer trace, or you can form it, the isocyanide, and that's the red trace. And you see here, of course, again, this is a cold molecular cloud. The temperature is very low. So therefore, any chemistry that occurs has to be barriers, and it has to be isothermal. And you see, in fact, this is the calculation shown here, which indeed indicates that the reaction that adds CN to benzene is exothermal barriers. Right? This is zero energy. However, to add CN in the isocyanide requires not one, but two barriers. And the energy to overcome these barriers is far in excess of the energy available to the molecules. So this path does not occur. And you see here on the far right this is Kai-Fu, who did a survey of TMC1, and we do a spectral stacking. You see there's perhaps weak evidence in this older work for cyanobenzene. This is the previous spectrum I showed you. And you see there's no evidence now by the same approach for its isotope. And part of the reason it's so much better now is we have a much bigger radio telescope, right? So it goes as potentially as a square of the collection area, and also the back end is we can now do very precise frequency resolution, better frequency resolution than was possible years ago. All right, so this is, from this one can.
Is this understood?
What's that?
Is this understood? Why the reaction path?
Why the reaction?
NC from CN to NC is so different? Is it because more electrons face hydrogen?
I'm not exactly sure. I mean, these are not huge barriers in some sense. These are kilocalories per mole. So this is, the order 10 kcal. But I don't know the precise answer as to why.
What would it
but
be?
generally, it's kind of what's that?
What would it be in Kelvin?
In what?
In kelvins. I mean, what temperatures? How much is that? 45
Oh, thousands. Yeah, thousands.
So it's a fairly large barrier.
Yeah, no, it's so large barrier. So the point being that the existence of this in the source tells us that this is convection. All right. So then the question is this the beginning or is this the end, so to speak? Right? Is this just a one-off experiment, a one-off detection where we have cyanobenzene, or is it possible now that there are other ring molecules we should be looking for? Right. So it certainly establishes unambiguously that there's primordial and aromatic chemistry occurs, perhaps, or at least exists in the source. You could argue maybe this benzene has been inherited from the previous cycle of the star or the molecular cloud, but nevertheless, it is there. And it's also very important because benzene is well known in the combustion literature and a wide number of calculations that the bottleneck to pH formation is formation of the first aromatic molecule. Right? So arguably, if this is here, potentially forming larger molecules may be easy. All right, so we in fact have two big projects for the GBT. One of them is called Gotham. It's kind of stands for GBT observations of TMC1 hunting for aromatic molecules. Anyhow, we have about 600 hours to look for different aromatic molecules based on this. But I wanted to return, it's part of the motivation for this series of experiments.
Did you pick the name or the acronym first?
Yes, we tried to do it. We tried to get something catchy. We also have ARCA, which is which is a search for aromatic molecules beyond PMC. All right, so that is kind of the motivation. So what we really want to do then in the lab is study benzene chemistry, right? We want to understand if we put benzene in a discharge, how does it fall apart? How does it grow? How does it isomerize? And there are 4 key people who've been involved in this whole complex mixture analysis, and they are shown here. So Kyle Crabtree was a postdoc in the group. It seemed like I almost say a year or 2 ago, but it's probably like 5 or 6 years ago.
Yeah. 7.
Yeah. So he was 7 years ago.
We're old mode.
Fairly recently, compared to my overall career. Anyhow, so he was a fabulous postdoc and did a lot of, as you'll see, a lot of work and built the design the spectrometer software, among other things, in addition to some of the techniques we developed. Maria Lean, who's a more recent postdoc, who's now gone on to CNRS in France, has done a lot of work as well related to this. And more recently, we have Brandon Carroll, who's responsible for this high-speed fitting algorithm I'll talk about, And Calvin, who he jokingly calls himself a regular postdoc, but in this, I think it's fair to say he's a super postdoc. He's done a lot of really amazing things. He's done a lot of this machine learning I'll talk about at the very end, so phenomenal postdoc as well. All right, so what we're going to do in this experiment is we're going to take, again, combine these chirp and cavity spectrometers. They both exist in the same chamber, so we can switch between them in about a minute. All right? And we're going to, again, strike a discharge. I'll show that in a moment. But this is, you don't have to worry so much about this, but we basically have a supersonic electric beam, and this, in the chirp experiment is here. We're going to synchronize the chirp with the gas pulse. Don't worry about the cryogenic buffer gas cell. That's an unrelated experiment, but very interesting in its own right. And we're going to also record a spectrum. And then we're going to switch over to a cavity, and we're going to do a variety of follow-up measurements. All right? And the properties are shown here. So the cavity, keep in mind, the chirp experiment has an IF bandwidth of order 10,000 megahertz. Right? So we're getting a tremendous amount of spectral information in 1 second. We're going to co-average to get better at signal pulse. The cavity, however, is only, 1/20,000th of that. It's half a megahertz instantaneous bandwidth. The dipole moment is not such a big factor, but again, we're in the weak dipole moment limit, so generally we scale this at dipole moment squared. So we will generally, the more polar the molecule, the more easy it is to detect in the chirp experiment. The line widths, as you see, the cavity is much sharper, so we can look at narrow structure and resolve it out much more easily. And the key point here is the chirp experiment is much more sensitive per unit time, per unit megahertz. Right? So there's an advantage of then covering this huge spectral range and then concentrating down on only those regions where there's lines. All right, so how do we make molecules? I talked a little bit about that yesterday. We use a simple pinhole expansion source. It's very expensive to implement, using very low temperatures, and it uses very little gas, very little of the organic vapor. It uses a modest amount of buffer gas. And this is literally what it looks like. This is a general valve. We have this little assembly on. So there's 2 electrodes. We pass the gas through. We strike the discharge. So by applying this on top of the general valve, collisions with electrons, there are a few EV energy. We drive this chemistry, we break bonds. We throw in the expansion before the adiabatic expansion occurs. Lots of chemistry happens. Fragments are made. Much bigger molecules are reassembled ultimately and often unexpected in neutral ways. And we see something that is certainly a very vivid example of something very large from something very small. Now, the point here is, as the expansion occurs, you rapidly cool, collisionally stabilize all this chemistry, and we do it in multiple minima on the potential energy surface. All right, so even though these molecules are locationally very cold, they can be up tens of kcals above ground. Probably the best example is there's 4 isomers of isocyanuric acid, which is one of the most first polyatomic molecules found in space. And there are 3 high energy sigma isomers that go up to isoformic acid, which is 84 kcals above ground. And with standard precursors, you can see all 4 of those isomers in our experiment, even though the location is very cold. Yeah.
You're locking them in the wells because they have.
Correct. Yeah. So there's a minimum on the potential, and then like the collisionally stabilizing them.
Right.
They can't escape. They can't. No unimolecular rearrangement can.
Right.
All right. I should point out, however, rotational temperature is not well coupled with vibrations. We can, in fact, cool molecules out in vibrationally excited states. This turns out to be a slightly subtle issue about how the vibrational energy is relative to the free energy. So we don't actually cool molecular vibrational levels that are low in energy or even high energy, somewhere in the middle, that we actually lock in. So,
What is the vibration cool? When it comes to supersonic or the aromatic expansion, what is that cool limit is?
in what degree of freedom?
Vibrational.
No, that's what I'm saying. It's not a ultimate. It's not. I mean, in the sense that it's. There are certain modes that tend to be frozen out, right? And they're not the lowest energy ones. They're not the highest energy, and they can be. You can have 2 modes sometimes that are close in energy. You won't see one. You'll see the other. So it's tricky, a little bit tricky in that sense. But it's just something to be aware of, that this is not very good. Well, it's quite good, but it's not as good as, it's not like a buffer gas cell where you're cooling at all degrees of freedom. All right. So again, this is a very simple schematic. This technique we call microwave spectral taxonomy is we're going to take a chirp spectrum. We're going to, in a perfect world, do it really fast. And then we're going to try to categorize it by different things. We could turn the magnetic field on. We could turn the discharge off. There's all sorts of different things we could do. The real point here is we want to do this double resonance. And double resonance, as I'll show you, is a way to connect lines in the spectrum to each other that can only arise if the molecules share a common upper or lower state from the same molecule, right? And what we're going to get out of this, obviously we can identify things that are known already, and we're going to get out locational constants. Okay, and we have to keep in mind we're not making any assumptions. There's no a priori constraints. We're simply just analyzing the spectrum and trying to find out what's there. All right, so this is. I missed this slide. This is spectrum that we recorded with the free spectrum. One is benzene plus O2, and one is benzene plus N2. Does anyone want to guess why we did these bottom two spectra? Thank you. Atmospheric gases. Because it's the dark secret of chirp spectroscopy, or even cavity spectroscopy, is contamination. Right? It's actually very difficult to look at water. Well, in Arizona, it's probably not that at all. But water and atmospheric gases. So it turns out when you make benzene, you have to actually take a small amount of ampule benzene. We put it into these tanks and we balloon it down. In doing so, it's very difficult to eliminate all atmospheric gases, nitrogen and oxygen, being the key point here. And so it turns out, as I'll show you, that when we did the benzene analysis, we came to realize that some of the lines were actually oxygen bearing. So instead of trying to deal with that, we simply recorded 2 additional spectra. And that's been very helpful. Again, the goal of which is we want to exhaustively analyze everything. So contamination. Anyhow, you see 480 lines here, almost 1,200 lines here, and 850. And this is signal flow. So you can see these lines are incredibly bright. They're 1,500 signal flows in some cases. And this is about 10 hours of innovation on each spectrum. So what we did in the first experiment with benzene is we wanted to optimize the chemistry on its isomer. You can't see benzene in our experiment. We turned the discharge on, we optimized the chemistry on benzene, which was known, but actually not measured at very high resolution, at least the resolution that we need. And then we simply record the spectrum in this period of time, right? It looks like a pretty rich spectrum, right? I mean, there's like 500 lines. But it turns out it's actually not rich at all, because what you see here is every feature you see is limited by the projector. These are razor sharp lines, right? So there's only 500 lines, right? So if I take this part of the spectrum, which is 1 gigahertz, and I blow it up for you, it looks like this. And then if I take 30 or 40 megahertz here, and I blow it up for you, it looks like this. So you can take the equivalent width of the full width and half max of these features. You know how many resolution elements you have, and you can calculate very easily the filling factor, the number of bright resolution elements in this experiment is about 1%. All right? So 99 times out of 100 of resolution elements are dark. That is to say, at least at this level of sensitivity, if we were to take our cavity spectrometer, we wouldn't see anything. And that's why this technique is so useful. It allows us to concentrate on all the bright things, so that in the cavity we can go back and instead of searching and only hitting a line every 100 settings of the cavity, we can then focus our cavity measurements on these bright features. So that's really, in my opinion, one of the key aspects. It allows us to do the cavity experiments very, very efficiently. All right, so again, the importance of double resonance. So if we have a line in the spectrum, and there are potentially other lines that it would be linked to, that is linking, saying that either shares a common upper or lower state. And this is just shown here in a very simple case, where, let's say, we're sitting on this line, we don't know in advance what that transition is, but there are other lines which can connect to it depending upon the properties of the molecule. All right, and these are the flexibles, right? Delta J Rho, plus or minus 1, and depending on if it's A-type, B-type, or C-type, we have very simple spectrums. All right, so there's only a finite number of possibilities that any line will be connected to another line. All right, so we're going to do this, again, this is the idea here, is we're going to do these binary double resonance tests. We're going to tune the spectrometer to one line in that chirp spectrum, which is unidentified. And then we're going to turn on a second radiation source broadcasted across the cavity, and spatially it overlaps and temporally it overlaps. And we're going to tune that second radiation source to this some unrelated, unidentified line. And then we're going to do an experiment. We're going to see if its intensity is altered by the presence of a second radiation source. All right, so this is an example here where we don't have the second radiation source present. And then we subsequently do these quick experiments, automated experiments, where we simply change the frequency of the second source, given this big catalog we have of unidentified lines. And you see what happens here is the line disappears. And that's because we're affecting the coherence, or perhaps more simply the population, by driving it very, very hard with this second radiation. Okay? And the beauty is this is really easy to do. It's just not optical spectroscopy, right? Or optical, it's much, much more difficult to do double resonance in this way. Literally, you have a commercial synthesizer, it's Ethernet programmable, and you program its frequencies. And these experiments typically, depending on the strength of the line, these are typically 2 seconds to do each experiment. Right? So you can pound through hundreds and hundreds of these combinations very quickly. Right? And when you see this, all it tells you is that they share a common upper level state. It could be this, it could be this, it could be who knows. Yes?
What's your power level for the experiment for the pump and probe?
So we're doing the cavity experiment, so we're optimizing the cavity on, we're optimizing the cavity power in that sense. For the double resonance, we can run up to 20 ppm,
Okay.
which is,
Yeah.
a lot of power. The problem, you have to be careful in the sense that when you drive the power that hard, there are potentially there's issues about baseline that can affect your FID, but as a practical, we usually run about 10 to 13 ppm. But my point is that's easily produced by key sites in this size.
Yeah.
So it's
Not
really...
so much from the terrorists.
No, exactly. So that's the beauty. This is really almost turnkey. All right. So this is what it looks like. This again, we're going to do these automated double resonance experiments. So we're sitting on this line at 8926, and we just churn through all these lines, and you see this depletion here. In the experiment, they're not color coded. I asked Kyle about color coding. When we change from one frequency to another, we'll see if that happens. So I color coded them for you, but they're not color coded. Right? And so that's what we would do. We would take a line and we would hit it with all 400 other lines, and we would go to the next line and you can do these tests, right? And this is what happens again. I'm repeating what I just said, but you have a DR hit here, where the line is bleached out, and then we have a couple combinations. And we ultimately form this one structure. All right, so this is one of the first examples we did with Kyle, and I think Maria, is we took a broadband spectrum of a stable molecule, which is wonderful because the whole lab smells like cinnamon.
That project was inspired by John Black.
Yes, that's true, yes. And so we weren't really interested in it, per se, in with all due respect, John, in the spectrum, but we wanted to show it was a nice proof of principle in the sense that we wanted to then do, so we did a chirp experiment, we probably did it for half an hour, I can't remember exactly. We got hundreds of lines. And then we did this automatic double resonance. So we tunes to the strongest line automatically, and it fits it with every other line. And we do, and the beauty is this is fully programmable. So you hit the button and you go home. Okay? So this took 19 hours. But that's okay, because the computer's doing it. We're not doing it, right? And it did, just to give you an idea, 11,000 measurements. Right? It's completely mindless. Right? But that's what computers are really good at doing. Mindless sense. And this is what the correlation, if you will, plot looks like. These are the points. I color coded them. They obviously they're all the same color, but you can see here that it's symmetric. Right? So if you, in theory, if you flip the order in which you did the experiment, you get the same result. Right? And so these actually, all these lines here are A-type transitions. Right? And there's no attempt to stop or have the experiment think about the result as it goes through. It just does, in this case, 11,000 measurements. And from this, you can invert the problem and get the rotational constants very easily, because you have so many double resonance here. In fact, I'll show you in a moment, you don't need nearly as many as this. All right? That's really the beauty of an automated system like this. All right? Whoops. So what Brandon has done recently, which is really a neat development is to automate this whole thing, the small number of possibilities that are consistent with these double resonances, right? So I said there are multiple combinations. And so what he's been able to do, or realized, is that matrix diagonalization is how we have to do these fits. And the way that's very slow, actually. So what you do is you pre-compute a grid of points from kappa of -1 to 1, which is from the prolate to the oblate limit. And then you vary the rotational constants in different deltas here, so to speak. And then you simply, the program determines from that what the spectrum is. It looks to see if the line that is connected by double resonance exists near that frequency within some threshold. And then it looks to see if the next line is there, also connected to the same way with the same threshold. And it runs through between 250,000 and 1 billion calculations in about 10 minutes. Okay? So it's super fast. It's 400 times faster than SP fit or peak over. So you can do this just like that. I mean, literally, right? So what's important here, let's say you have a grid of 25. If you have about 4 double resonance hits, certainly by 5, there's only one solution, effectively. So you can, within 5 double resonance hits, let's say, you can ultimately determine the rotational constant of the molecule. Right? Yes?
Did you parallelize the code?
We're in the process of doing that. So we did it, you know, we have some high-end computing resources. We could probably do this in a fraction of even that time if we parallel.
So this work is done on a single core.
Yes, yeah. So that's what he's doing a lot. He's really trying to refine this and work on the user interface. But yeah, it should be instantaneous. I mean, that's one, you know, you can imagine doing an experiment. As it gets to DR hits, eventually it's going to tell you the answer, right? It's going to be all linked together. Again, there's no a priori information. We're just brute force figuring out what the carrier is, what the rotational constants are of these molecules. All right, so this is an example showing you some of the outcome of that approach. I should point out, let me first show you what most interstellar molecules look structurally. So this is the asymmetry parameter. Asymmetry parameter is defined in ratio combination of different rotational constants. The prolate limit is kappa of -1. That's where you have very little mass off the axis. And it's essentially a linear or nearly linear molecule. And the lines, the rotational lines you observe are ratios of integers, which by eye, it's easy to pick out. And that's why those molecules are often often easy to find, and also the same is true in space, right? And so most of the molecules found in space, with about literally less than 10 exceptions, are very close to the prolate limit, right? The other limit is the oblate limit, and that's like literally a pancake, right? That's a, a frisbee kind of style, right? And so there are very few molecules, certainly after more than a few atoms, that are in this category. And that's not because, again, the rotational constant. If you have a linear molecule, you need one rotational constant. You have a planar molecule, you need 2. You have a 3-dimensional molecule, you need 3. Right? It's really not that complicated. But combinations are what make it difficult to pick out in a forest of lines. And so this here, don't worry so much about this is the log of the absolute value of the defect is an indication of how far out of the plane these molecules are. And you see that many of the molecules that we found by this approach are very far. I mean, there are many that are near the prolate limit, but a number of them are not near the prolate limit. They're much more oblate molecules. And I should say blue are oxygen molecules we found, green is nitrogen bearing, and red is hydrocarbon. Yes.
Do you think it's because of the patterns, or do you think it's because sample bias? Because we've been looking at chains and things like that for so long, or do you think it's because
I think it's a combination of things. I think it's dipole moment, which generally favors linear chains. I think it's also just the fact that those are just so easy to see in the laboratory and in space.
Right.
So I think if we have, along the lines of what we and other people are doing, to just have the computer figure out these unusual molecules, unusual structures, potentially that can ultimately be used to really probe things where it's not so it's much more out.
because the field's kind of had a history of oh, I saw this thing, let's stick another medical group on it.
Absolutely.
For the next
No,
bigger.
exactly.
And so that tended in the direction of looking for
Correct,
chains.
yeah. No, it's a self-reinforcing kind of.
Right, and I wondered about the dipole moment, because that's what,
Yeah, I mean, dipole moment is
Yeah.
certainly a big.
yeah, okay.
So, we did, I would estimate at least 600,000 additional measurements. So, now these are automated. They all, not all, but some of them take 2 minutes, 2 seconds to do each one. Some of them take 2 minutes. But a lot of follow-up measurements were taken after the 10 hours for each of those. And several months, perhaps more than several months, but we're done. And this is what the spectrum, after we've now removed all of the assigned lines, right? This is what the spectrum looks like. Right? That's the same scale as the previous one. Okay, now I'm going to blow it up by a factor of 20 because it's not perfect by means. But it's really pretty good. Right? So this is what's left. And that was, it was 482 lines or whatever it was. There are 57 left, and you can see, I mean, again, signal to noise, there are a few of them that have, again, this is after 10 hours of integration of mature. So these are fairly faint lines. Again, the strongest lines in the benzene were 1,500, so we have a few of them around 50 or 60. In the nitrogen, it's again quite low, about peaks are about 20. So if we summarize, what have we found? Well, what have we found? This is the summary of the results. So all this work is really distilled down into this table here. So we have frequency range, we have 2 bands that mostly concentrate on this lower band, but we have higher band emissions, all 3. The number of features that we've observed, the number that we've assigned, and the percentage. It's actually, this is outdated, it's in the low 80s now, but we're typically getting mid to high 80s of just the features that we've assigned. And so we're getting close to 90% of all the features that we've observed in the individuals. By assigned, I mean we know it's associated with a molecule. I don't necessarily, as you'll see, in every case, what the molecule is here. All right? If we talk about the intensity, again, total intensity, unassigned intensity, we're in the mid to 95%. So we've assigned nearly all of the spectral intensity. The number of unique species is listed here. So the richest discharge is benzene O2. There are 130 different molecules that we found. And if you add in isotopic species and variants, it's actually, again, this is outdated, it's about 170. Okay, so there's nearly 100 to 200 different individual molecules if you also want to include isotopic species in this spectrum, which I'm not surprised by, but this is a little frightening at the same time. And so this is then just some of the statistics here. This is shown on the left is the total intensity, the molecules that are responsible for the most intensity in the 3 discharges, and the molecules that are responsible for most number of lines in discharges. And you see here, so in terms of intensity, cyclopropionylidene, 623H2, is very, very bright. But it's followed by the total intensity is something larger than benzene. It's phenyldiacetyl. All right. In fact, the number of lines, just by number, about 10% of all the lines in the benzene discharge are due to phenyldiacetyl. Right. So this is a molecule larger than obviously benzene, and we see some other things as well. In terms of O2, we have this previously not observed, but ortho and para C6H6O. It's very, very abundant, as well as and it's responsible for many of the lines. And not surprisingly, the aforementioned cyanobenzene or benzonitrile, depending on how you want to refer to it, gives rise to the most intensity and the most number of lines that we have found in this discharge. All right. So, although we've detected many molecules, we don't actually know in a few cases what their actual elemental composition is and structure. Remember, this is completely brute force. We're simply taking these lines, we're connecting them together, we find a rotational constant, we then can extend the spectroscopy in higher frequency with our cavity or even go. So we have tens of lines for all these molecules. We have an unusual naming convention. Some of them are supers, and some of them are U molecules. But these are the rotational constants. These are whether or not we saw an A-type transition, a B-type transition, and even a C-type transition. So this molecule here, U-mol 1499, I think we have 60 or 70 lines in the cavity, and it's chiral. We don't yet know actually what the molecule is that's responsible for that. But we know it's certainly produced abundantly in the discharge. So that's then becomes a question of how do we take that information and actually get it into science. All right, so just again to show you some of the new species, entirely new, never measured before at certainly potentially any wavelength, are all of these molecules here. There's various isomers, syn anti-isomer of benzene, there's these various fragments. We see, again, the aforementioned phenyldiacetylene. You see these 5-membered rings are quite conspicuous as well. And you see I've shown here whether or not we're adding carbon or subtracting carbon or adding. So in fact, we see roughly half of them are bigger than benzene. So that's not perhaps a surprising result, but an indication that benzene growth occurs very fastly under our conditions. We've detected many oxygen bearing. I actually ran out of time, so I'm just showing like 6 of the 20 or 5 or so that we have here. These ones here are very, very abundant. I mean, these are super abundant in our, they're so abundant, these C6H6O isomers, we can see the carbon-13 of them in natural bonds. Right? So they're down by, again, almost a factor of 100. These are a few others as well. And then we've seen various nitrogen. Again, I didn't show them all here. You see the phenylcyanobenzene here. We've seen these 5-membered rings with a CN group, kind of analogous to benzene nitride. And we've seen others as well. So we've in total probably seen 50 molecules, new molecules, and these are not including the ones that we've yet to assign. And we've measured many, many more at high resolution. For the oxygen bearing, as you probably saw there, the oxygen is almost always kind of terminal to the carbon chain. It's terminal to the ring, right? And we generally, with oxygen, we don't see very few species that are actually larger, have more carbons than benzene itself, suggesting that, again, that's why you burn things, right? Burning produces ultimately CO2 and water and things like that. So we don't see a whole lot of growth when we add oxygen to the mixture, but certainly with benzene, and N2, we see much more growth. The heteroatom, as I already alluded to, is almost external to the ring or to the terminal position. We see, in the case of the oxygen species, a few molecules that have 2 oxygens, but they are fairly weak and only a few of them. As I already pointed out, species heavier than benzene are fairly common in all of them, certainly in the nitrogen and the normal benzene. And what's particularly interesting, again, these ring chain molecules, yes?
You said most of these molecules are terminal oxygens.
Yes.
Not really an insertion into the ring.
Correct.
If you started with something that's not already cyclic with benzene, you start with something like hexane or already a chain with oxygen, do you think you'd see insertion?
Like we start with furan or something like that. The oxygen is already in the ring.
Or something along those lines, just something, a different structure other than benzene, maybe not already cyclic. I don't know.
I don't know, actually. That's a good question. I don't know the answer, actually.
Because if you wanted the oxygen insertion products, you could potentially start with
Yes, indeed.
already under the chain.
Exactly. No, it's a good question. Yeah, absolutely. I mean, we did 30 hours of experiment. So keep in mind, there's a huge amount of now that we've done this, for example, we could do that experiment, and it would be far easier because we have all of these, many of these things already identified. But yes, but again, we started with O2. There's other oxygen sources as well. Just to finish my thought here, so these ring chain molecules are very prominent. The question then is, perhaps that is an important pathway to pH growth in our experiments. All right. So I'm not allowed to say what the molecule is, but you can then take this huge data set, and you have all these molecules with very high spectral resolution. You can do all the spectral stacking, just like I showed you for cyanobenzene. Turns out almost all the molecules that we think of as well characterized, like pyridine, vinyl, furan, they're actually not measured at sufficient resolution for TMC1. They were measured years ago, typically in a warm gas cell, and the line widths and the spectral resolution is at least an order of magnitude poorer than what we need. So we now have systematically remeasured all of these molecules as a course of this project at the required resolution. And then we can properly do this spectral stacking. Right? So we take the present data and we take where we are in the Gotham survey, which is approaching about 50% now. We can do the spectral stacking. So this is 2 molecules that contain nitrogen in the ring, right? And we stack the data, and there's no hint of hydrogen. This is kind of interesting because you see cyanobenzene very well, right? And this is cyclopentadiene, you don't see it either as well. I can't tell you the molecule, but we have a ring molecule where we do the same spectral spectrum, we have a ground state, and it's observed. It's observed actually quite, with good signal to noise. There's a high energy isomer, but there's no evidence for that as well. So again, it's an example where we can take all this data and we can just literally, so to speak, throw it against the wall, in this case, throw it against, and look for these molecules. So what's interesting is perhaps that's telling us that we are inheriting these molecules, that we're not getting the nitrogen in sick designs. Formed in the ring, the CN seems to be often external to it. But that remains to be seen. Further experiments and observations are needed. All right, so machine learning, let's get spell. It's not really the focus. I'm not going into very much detail at all, but a big part of this effort now has led to the idea of machine learning and how we can apply machine learning to rotational spectroscopy. So the information age, as you see here, is upon us, right? And that's certainly true of rotational spectroscopy. In space, or in radio telescopes, everything is broadband now. In laboratory, we're always broadband. It's not a question of getting information. The question is converting information to knowledge. And the robots are indeed coming. They're not here yet, but they're coming. And the question is, how are we going to deal with this, right? We're going to get all this data. We're getting all this data from all mine. And perhaps we're going to throw most of it away. I don't know. But potentially, there's more science we can do. But there's also potentially a lot more work that has to go. So what we really want to do is let computers do what they do best and try to take what is several months of work I showed you and hundreds of thousands of extra measurements. And is it conceivable we could move much closer to real-time analysis of a rotational spectrum, even though we've not measured these molecules. And so the idea here is going to use modern computing. They're really good at computing. They're not good at making decisions. And then we take the humans, which are really good at interpreting and decision makers, and analyzing the spectrum. So there's really two key points that we need machine learning to help us address, and that is spectral separation and molecule identification. So the idea is which frequencies belong to each other, and ultimately what are their spectroscopic properties. On the basis of these spectroscopic properties, we can plausibly infer the molecule, or at least constrain considerably the subset, the parameter space that the molecule might consist of, and what its structure might be. All right. So
what does it mean? Which frequencies belong to each other? Belong to a set?
Well, so again, we have this complex mixture. We have multiple lines in the spectrum. Can we pick out the lines?
How they are correlated?
Correct. That they're correlated. That they come from the same molecule. So if we, that's vast majority of what we did in that benzene project is figure out what lines in the spectrum were correlated with each other. All right. So we're not the only people who thought about this. There was a paper in 2018 where they developed a fairly simple artificial neural network and trained it on a few thousand different systems, molecules, and the idea was to automate fitting of rotational spectra. They developed a classifier which simply determined from the molecule whether it was linear, symmetric top, or asymmetric top, what the spectrum was, and then they did linear regression to develop the most likely parameters. So this was, I think, an important step forward, but there are, of course, a number of constraints. First of all, it only could handle one spectrum at a time. You had to have a single spectrum, a single molecule. You couldn't have any interfering features. And of course, we're interested in these complex mixtures where we have tens of thousands. And keep in mind that these artificial neural networks don't understand the underlying physics, right? They simply are only aware of the problem, so they don't conserve things like energy as a general rule. All right? So, in some sense, this is an indication that there may be great value in thinking of these in a Bayesian approach where we look at probabilistic models, right? We have limited information, and we want to try to solve things by inference rather than deterministically. So the idea is that if we have a modest amount of information, what's the likelihood of X given Y, right? So we want to evaluate the conditional likelihood of all possible outcomes, and then use that to guide us in further measurements. And the same kind of thing. What is the likelihood of a set of frequencies belonging to a molecule having given well? So we actually developed a classifier as well. This is, again, really the work of Calvin Lee, and which we took a spectrum and we were able to develop a neural network, and it was able to distinguish A-type and B-type and C-type transitions. So this is now getting probability. We're not getting just one estimate for one solution. We're getting probability. It's hard to see this here. So the probability of, in this case, of a B-type transition is 100%, 0, and 0. So and we can also deconvolute this fairly well. So it's actually fairly encouraging. So the idea is, I won't go into detail here, but the idea is we're going to take potential parameters, we measure A, this will only be based on what we measure. We pick A, B, and C. We don't measure that at the moment, but we know whether it's 0 or not. And we know the inertial defect and the kappa. And we ultimately want to encode it with these canonical smiles, which is a one-dimensional representation of the conductivity of the molecule. Right? So we take the moment's inertia, and we create these network to do all this. And so the probabilistic molecule identifier takes the information, experimental spectroscopic information, and ultimately tries to infer the stoichiometry, the structure, and the functional. All right, and that's why, in fact, we've developed this big database, and we're really interested in the uncertainties in the calculations. So this was serving not only as a lookup table for the new molecules we found, but also as a training set for the machine learning. Again, and we calculate these things fairly quickly. We ultimately are going to use even larger structured databases to try to make the training set more complete, cover all of the parameter space here. And so I won't go into too much details, but Calvin's been working very hard on this, and you take these spectroscopic parameters, you run them into the spectroscopic decoder, and then you try to decode not only the formula, but the functional group, and ultimately the smiles. And this is at an early stage, but it does look promising in that he is now shown here are 4 examples. This is a somewhat complicated plot, but on the left is the so-called violin plot of the composition, and these are different functional groups. So does it have a CH, a CNO, CN, or CNO? And in fact, again, it looks somewhat promising. More complicated molecules which have multiple functional groups, this in fact properly predicts 6 of the 7 while folding the other ones. In fact, are likelihood, it's more likely to predict, in this case, the correct functional groups. So we'll have to see how this goes next year or two, but I think it is a promising move and really capability of using computers for good. That's what people do. So the idea is we're starting with these spectroscopic parameters. We want to move to a picture of the molecule. We can do these deep learning models now, computation efficient, about 3 seconds per molecule. And we want to ultimately implement this so that we don't take months and months to analyze things. We can do it much more quickly. And potentially, we think it's possible to do it 100, perhaps even 1,000 times more quickly. So with that, I will end because it's out of time and I'm out of material. So thank you. Questions? John?
I gather in some cases you see that you identify molecules in more than one vibrational system.
Absolutely, yes.
And do you have any way of establishing the absolute vibrational quantity?
Well, in that case, we're using, our identifications are tentative in that we can normally identify them because their locational constants are so close to the ground state. And then we're working with people like John Stanton, and he's systematically calculating all of the molecules for which we believe we have the vibrational. Well, eventually, he's calculating the alphas for us. And in about 60% of them so far, we have what we think are really firm identifications in terms of the vibrational mode and its form. But they're typically, again, these modes that are around KT, and we often will see a progression one following.
And the next question is, I'm just wondering, in principle, if you could apply the same kind of philosophy and identification procedure to very broadband infrared spectra.
Potentially, yeah. No, I mean, that's our goal.
High resolution infrared
yes.
spectra.
I mean, our goal in the end is we have the advantage in the lab, we can do various experiments and we can be confident in things, but it would be really, you know, amazing. The ultimate goal would be to take a wide band astronomical spectrum, right? And the question is, could we apply these techniques ultimately to that problem? But the infrared is also, you know, it's the same basic idea. So it's too early to tell how successful or how big an effort failure that could be, but it's certainly, the capabilities are there to test these.
So many questions. So when you calculate the rotational constants for the unknown species, are you using something like AutoFit for that?
No, so in the end, so one limitation of Brandon's current program is it doesn't, it only solves the original program.
Okay.
I mean, there is no CD incorporated into it.
Right.
So what he does is, for example, there's two ways to do it. One is, I mean, the most common way to figure out the correct identification is he takes the 3 or 4 or 5 double resonance hits,
Yeah.
calculates a spectrum, and then looks at the unidentified lines and can determine which ones are also predicted based on that small
Right.
data set.
Right.
The problem that is beginning to fail is because it doesn't take into account the CD.
Yeah.
So that's the next level is for his program
Yeah.
to account for that. But ultimately, what we're doing is we're using the cavity measurements, which are much more precise by a order of magnitude. We fit those using SP fit, and then we predict the rest of the spectrum, and then an automatic
Yeah.
capability measure as many lines as we can. So
Right.
even though there may be 5 lines in the chirp spectrum, we may have 50 lines in the cavity.
Right. So I was also wondering, for your database, how did you choose the molecules that you calculated to build your library?
He's used something called graph theory, where you start adding these molecules. I mean, we have realized there is some problems that we want to, for this to be correct and rigorous, we need to fully sample parameter space.
Right.
So the problem is there are some functional groups for which there are many more combinations for
Right.
other functional groups.
I just wondered if you've looked at the NIST computational benchmarking database, because a lot of things are in there.
I don't know for sure, but I suspect Calvin's looked at
Okay,
many
that's
of
just
them.
an
Yeah,
idea if you-
he's looking at a lot of these biochem also huge databases.
Okay,
But yeah, it's a matter of making sure that you're properly sampling
right.
the parameter space.
And last but not least, have you looked at other types of sources besides TMC1 for the benzene derivatives, like, say, CRL?
Well, so what Andrew Burkhardt, who's leading this ARCA project, is looking at cyanobenzene, benzonitrile, and other sources.
Right.
And that's proved to be very, we have a lot of results. We have,
Okay,
essentially every single source that he's working, we've seen is evidence for benzene.
okay. I just
So we
wondered,
have,
like,
like,
IRC 10216 and...
No,
like, there's
no,
all these-
we've, mostly it's, pre-stellar cores.
Okay.
I mean, they're fairly early in the star formation phase, but
Yeah.
the goal is to keep.
I'd be curious if they showed up in the sources where you see C60, C60 plus,
Yeah.
and C70. Yeah.
I'm sure Patrick's probably looked for
Probably.
my try.
Yeah.
Hard to see. And if he had found it, we probably would know better. But, yeah. Yes.
It seems to me what we call machine learning is more like search and sort. The algorithm really is not learning. I mean, machine learning is most efficient as an optimizer. It learns how to optimize the process.
Correct. Yes.
But what is it learning?
Well, it's learning ultimately the correlation between structure in this case. And
And can you tell you, for instance, now go look at this molecule and you will find this. That's what to me is machine learning. In other words, from a set of database of lines and molecules you've given it, it can learn based upon relations between the dipole moments, vibrational energies, rotational levels. It can tell you, for instance, go look at this molecule, this is what you find. That would be
Okay, well, we're using it in the way
we're
of.
using the search and sort, which is, I think.
Well, no, I wouldn't say, we're not searching or sorting. Exactly. We are training it on a very large data set.
Yes.
And we are then, on the basis of what it learns from that data set, we're asking it then, on the basis of very limited data, to give us probabilities of.
I mean, this is, like short algorithm for quantum searches and over for sorting, things like that, or of course, well, no,
Yeah.
you can implement valuable, but it would be useful, for instance, if you actually learned something. That is the machine.
Yes. Well, yeah, that's the question, what exactly is learning, but, yeah. Yes.
How many parameters did you use for the machine learning?
How many parameters? I forget how many layers, I forget how many layers and how many parameters he's using. I wouldn't want to say a number because I'd probably be off by a factor.
So you are still using an artificial neural network for the machine learning?
Yeah. Other questions?
I guess it's kind of follow up. Based on your memory, do you think it's larger than like 8 parameters? I think.
Oh, and then I suspect so, yeah. Okay.
Why 8?
Like the number of parameters used for training.
Why 8? 2 to 3.
Have those information error cycles also been for any other sources?
No. I mean,
So,
we've only looked for them in TM2.
okay.
No, because the other project is focused on yeah. So we haven't had the chance to put in a proposal to extend more generally, but at least one or two of these sources, benzonitrile is actually easier to detect than it is in TMC. So that is perhaps very encouraging for other Yes.
Do you have any ideas on how we actually design the structure of the neural network? I feel like that's one of the really fun, quote unquote.
I would have to defer to Calvin for the details on this, and he would be glad to talk to you at length about his neural network. Because he's really, in the past, I'd say 6 months, he's really taken off with this whole machine learning thing. It's producing pretty results. I'm optimistic. All right, no
No
questions?
questions?
Let's thank this week.